Hello, Physics 20s. In today's lesson, we are going to continue to look at problems that deal with centripetal forces. Although for the problems we're going to look at today, we're going to look at circular motion that is occurring exclusively in a vertical plane of motion. And just to quickly clarify what I mean by a vertical plane of motion. So let's say that we have the ground. Vertical circular motion would be in a manner in which the motion of the circle is perpendicular to the ground. So if I drew an object in vertical circular motion with respect to the ground from the side view perspective, vertical circular motion would look like this. So the Ferris wheel we see in the background of the PowerPoint, that would be undergoing vertical circular motion. Horizontal circular motion, we'd be dealing with motion in a plane that is parallel to the ground. So that's what we did last time. So that would be motion like this. Our object goes around a circle in a horizontal plane. No need to restate the learning outcomes as they are identical to the one from the previous lesson. So we'll just go right into 3 example problems. First example, I have a 1.8 kilogram object is swung from the end of a 0.50 meter string in a vertical circle. So that could be a rubber stopper attached to a string. And I given the period of revolution as 1.2 seconds, and I want to A, calculate the magnitude of the centripetal acceleration, B, prove that the magnitude of the tension in the string is greatest at the bottom and smallest at the top. And then C, I want to go ahead and calculate what the magnitude of the tension is at both the top and the bottom of the circle. Okay, so let's start off with the easy parts. The easy part just wants me to do a calculation for centripetal acceleration, the magnitude. We are given the period. So the magnitude of my centripetal acceleration, AC, is equal to, and we can just drop that magnitude absolute value symbol with the vector sign and just write down AC. We'll take the part of the equation that has the period in it, so that's the one that has 4 pi squared r over t squared. And then we're going to plug numbers into that equation, so that would be 4 pi squared times r. R is 0.50 meters. Divide this by the period squared, 1.2 seconds, all squared. And then that would give me a centripetal acceleration magnitude of 14 meters per second squared. B says prove that the magnitude of the tension in the string is greatest when you're at the bottom of the circle and smallest when you're at the top. Okay, so let's start off by drawing a free body diagram and mass acceleration diagram to represent the motion. So I'll do a free body diagram of this object at the bottom of the circle. And the corresponding mass acceleration diagram. And let's just use a dashed line to represent what the circle looks like. So I'll just choose to do this in purple. So let's say this is the center of the circle. Same thing, we'll do the center of the circle here. And just like before, I'm going to start off with the mass acceleration diagram. I find the mass acceleration diagram is helpful in identifying what the forces look like in terms of how they're unbalanced. Okay, so we're at the bottom of the circle. So I'll draw my mass here. Label it as M. And at the bottom of the circle, your centripetal acceleration is center seeking. Therefore, at the bottom of the circle, your centripetal acceleration would be directed upward towards the center of the circle. Now here, at the bottom, we actually have a couple of forces that are acting on the mass at the bottom of the circle. If you were that mass, you would have your weight that is pulling down. So this is the big difference between the horizontal circle problems and the vertical circle problems, is now we have to look at the force of gravity, because the force of gravity is in our plane of motion we're looking at. So we'd have our force of gravity pulling down, and we'd also have tension in the string that would be tugging on us towards the center. The reason I want to draw the mass acceleration diagram first is because it tells me which of those forces is bigger. So I'm going to have an applied force up and the force of gravity down. Since I have acceleration towards the center of the circle, it means my net force must be towards the center. The tug-of-war winner needs to be towards the center. So what that means is, in order to have a net force towards the center, you need to have your applied force, which I'll call FA, larger than the force of gravity, Fg. I could have exaggerated that more so, but hopefully on the FBD that you see here, you can see that my force applied is bigger than the force of gravity, which means there's a net force towards the center of the circle. That's my centripetal force, that net force. And that's confirmed because the acceleration is also towards the center. Let's go to the top of the circle now. FBD at the top, and my mass acceleration diagram. Once again, I will start off by sketching what the circle looks like. Okay, so we'll use that little plus symbol or that crosshair to represent the center of the circle. Again, technically on a true free body diagram, you would not show the circle's trajectory. I just draw it because I find it helpful in just visualizing what's going on. But again, that's why I'm doing it with a dashed line. Okay, so let's go back to red. All right, so let's do the mass acceleration diagram first. Now we're at the top of the circle. And then my acceleration is center seeking. Therefore, it point towards the bottom of the page. And then go to the free body diagram. At the top here, we have the same two forces, an applied force and the force of gravity. The force of gravity is down again. And this time around, if you were that rubber stopper or that object, you'd feel the tug of the string pulling you towards the center. So your applied force in this scenario would also be downward. Okay, now the question wants us to prove, this means mathematically, the magnitude of the tension in the string is greatest at the bottom and smallest at the top. We could actually provide a qualitative justification for this right now in terms of why is the tension bigger at the bottom compared to the top. Well, look at the bottom of the circle. At the bottom of the circle, the applied force has to work against the force of gravity. The force of gravity is not assisting in making the object go around in a circle. It's not pointing towards the center of the circle, only FA is. So FA has to work extra hard to provide a net force that's towards the center of the circle. If you compare it to the top of the circle, well, FG is helping now. Both FG and FA are pointing in the same direction. So because FG is helping, the magnitude of the applied force can be a little bit smaller in order to provide the exact same net force towards the center of the circle. So that would be a qualitative justification as to why tension is larger at the bottom and smaller at the top. However, we're going to show this mathematically, and we'll do that by deriving some equations of motion. Okay, let's do that on the next slide. So let's break the page into two parts. We'll do the bottom And we'll do the top over here. Okay, at the bottom of the circle, we're going to say, let's choose up to be positive. I'm going to find the sum of we're going to say sigma FC because we're dealing with forces in this center-seeking direction. So sigma FC is MAC. Okay, let's go back to the free body diagram and look at this. So assuming up is positive on the free body diagram at the bottom of the circle, since FA points up, it's positive. FG points down, it is going to be negative. So this part of the equation would turn into FA minus FG is equal to mass. And at the bottom of the circle, the acceleration points upward, so that would be positive. Centripetal acceleration. And then let's expand the equation of motion. So we'd have FA minus mg is equal to MAC. Let's bring this mg term over to the other side. So if I do that, I would then have FA is equal to MAC plus mg. And I'm just going to do one more step. I'm going to factor out the common m, and I'm going to write down FA at the bottom is equal to m AC plus G. And we'll box this equation. Maybe just call it equation number 1. Okay, now we need to do the top of the circle. Now, I'm going to change things up a little bit. So far, when we've been writing down equations of motion, we have always been saying that up is positive, down is negative, right is positive, left is negative. And the reason we've been doing that is we just wanted a starting point for being consistent with positive and negative. So we just use the Cartesian plane where the x-axis is positive towards the right, negative towards the left. The y-axis is positive up and negative down. It turns out, though, that you can choose whatever direction you want to be positive. So you don't always have to say up and right or positive. If it was more convenient for me in a certain problem, I could actually choose left or down to be the positive direction. What I'd recommend doing is because I find that students, one of the biggest mistakes they make is they often forget to include the direction of acceleration. So what I would do is go to your mass acceleration diagram and then identify what direction the acceleration points and make that the positive direction. So at the top of the circle, down is the centripetal acceleration. Let's make that positive. If we make that positive and we write our equation of motion, both FG and FA are going to be positives. So odds are if you choose whatever direction you accelerate to be positive, you're going to have more forces in that direction that are also going to be positive. So let's switch it up here. Okay, so we're going to say down is the positive direction. I'm going to write down the sum of my centripetal forces is equal to mass times centripetal acceleration. If down is positive, well, both FA and FG point down, so they would be positive. You'd have FA plus FG would be equal to mass times, well, we chose the direction we accelerate to be positive. Let's expand this a step further. We'd have FA plus M times G is equal to MAC. Let's get the FA by itself, subtract mg from both sides of the equation. Then you'd have FA is equal to MAC minus mg. Then one more step, let's factor. And then you'd have FA at the top would then be equal to MAC minus G. We'll box that, and we'll call it equation number 2. Now, about that positive direction, if you did still want to make up positive, just be aware your equation of motion. If I made up positive, would then be negative FA minus FG is equal to negative MAC. If you multiplied the whole equation by -1, it would just turn into the equation of motion I would get if I had down was positive. So it just makes it a lot easier, and it's a lot more clever just to choose the positive direction to be whatever direction you accelerate. So I would do that from now on. Okay, now in terms of, we want to prove mathematically why is the tension in the string greater at the bottom compared to at the top. Well, look at my two equations. They're almost identical in format. There's just one thing that is different. The one thing that is different is the sign in front of the G. In this equation, we're adding G. In this equation, we are subtracting G. So if I'm subtracting G, that's going to make the tension at the top smaller. I suppose if I wanted to write this down in like a complete sentence to clarify why this is the case, so I could say FA at the bottom is greater than FA at the top, since, compare what you see in brackets. Since for equation 1 in the brackets, AC plus G would be greater than AC minus G. And again, that's the only difference between those two equations, is that single sign. So since you're adding G here and subtracting G there, the tension must be bigger at the top of the circle if you do it mathematically. Part C, now we're just going to plug numbers in and calculate what the tension is. Okay, so FA at the bottom would be equal to, the mass is 1.8 kilograms, multiply by the centripetal acceleration, which we got as 14 meters per second squared. This one we add 9.81 meters per second squared. And then FA at the bottom would be equal to, again, this should be the larger magnitude, and I get 43 newtons for this one. Box that answer. At the top, FA at the top would be equal to, plug the numbers in, 1.8 kilograms times AC, which is 14 meters per second squared, subtract 9.81 meters per second squared. This is going to make FA at the top smaller. Which we know to be smaller because the force of gravity is helping that applied force out and providing the same centripetal force, net centripetal force. And then we get FA at the top is 7.5 newtons. So this is something that's quite a bit different for vertical circular motion problems compared to horizontal circular motion problems, is depending on where you are in the circle, specific physical quantities can be different. We can see that here when we calculated both the tension at the top and the tension at the bottom. Next one. We have a 900 kilogram truck, moves at a speed of 16.0 meters per second, riding over top of a frictionless hill. I'm just going to sketch this. So let's draw our hill. At the top of the hill, we're given the radius. We want to calculate the centripetal acceleration magnitude and also the apparent weight of the truck. Okay, so first of all, I just want to clarify why this is circular motion. You could model this little bump in the road here as being an actual part of a circle anyway. So I could draw like the center of the circle here, and then if I just sketch the circle around, that little bump in the road, part of it is circular motion. So we can use circular motion to mathematically model this problem. The apparent weight of the truck. We had that problem back in dynamics on the vertical acceleration lesson where we talked about calculating the reading on a bathroom scale. The apparent weight is kind of like the weight, the force that the ground would have to push back against the truck. That's a better representation of what weight actually is. We can better define an object's weight based on what normal force is pushing back on the objects. We're going to call this Fn. That's my apparent weight. Okay, so easy part first. Okay, so I want to calculate the centripetal acceleration magnitude. This time we're given speeds. We'll use the centripetal acceleration equation that is Vc squared divided by r. Plug numbers into the equation, 16.0 meters per second all squared, divided by r, which is 50.0 meters. And I get my centripetal acceleration would be, and we're going to 3 significant digits, and I get 5.12 meters per second squared. Okay, box that answer. B. Okay, we want to know what's going on at the top of the hill. Okay, so let's draw an FBD. At the top. And then we'll do our mass acceleration diagram as well. And we'll start off once again just by sketching what the circle looks like. So there's the center. Do that for the mass acceleration diagram as well. Actually, I need a bit more space here, so I'm just going to I make this circle a bit further down. Sorry, I wish there was a quicker way to erase the image without erasing everything on the screen. Okay, yeah, let's go back here now. Purple. Okay, yeah, I'll make it a bit further down. So here is the center of the circle. You'll see why in a moment why I did that. Otherwise, I would have had my forces going through the FBD acronym, or one of the forces going through them. Okay, again, my recommendation is always start off with the mass acceleration diagram. I would do that whether it's a circular motion problem or a dynamics problem. So it always communicates to you how you should draw your force vectors. Okay, so at the top of the circle, my centripetal acceleration would be towards the, again, it's center seeking, center of the circle, which is directed vertically downward. At the top of the circle, if you were the truck, you would experience 2 forces, your weight pulling down, and there would also be that reactionary force from the ground pushing back against you. That would be up. Now the question is, which of those forces is bigger? Well, look at your mass acceleration diagram. If my acceleration is towards the center of the circle, it means my net force, or my net centripetal force, also must be towards the center. So my tug-of-war winner must point down, which means that the force of gravity, Fg, should be larger than the normal force. Tug of war between Fg and Fn. Fg is bigger, which means the net force is towards the center, and that's confirmed by the acceleration also being towards the center. Okay, let's be clever about what direction we want to be positive. Again, what I would do from now on is choose whatever direction you accelerate to be positive. So I'm going to say let's make down positive, and look at the sum of my centripetal forces, and that's equal to mass times centripetal acceleration, and that's your circular motion physics principle, which I believe is numbered 2 on your formula sheet. Okay, if down is positive, then that means Fg is the positive force. Fn would point up, which is actually negative, and that's equal to m and then positive AC. Again, if you choose up to be positive, the signs are just going to be opposite. But if you multiplied the equation by -1, it would just turn out to be the exact same equation anyways. Okay, we want to get, well, let's expand the equation of motion first. This would be mg minus Fn is equal to mac. We want to get Fn by itself, so let's have Fn and the mac flip spot. So I'll add Fn to both sides of the equation and subtract mac from both sides. So when I do that, and I want to write down the variable I'm isolating for on the left-hand side, that would then be Fn would be equal to mg minus mac. We can take this one step further and factor. Again, I like to sub in as little numbers as I possibly can. So you have m and then g minus ac. So then your Fn would be equal to the mass of the truck, 900 kilograms, multiplied by g, the magnitude of g, 9.81 meters per second squared. Subtract the centripetal acceleration magnitude, 5.12 meters per second squared, and then I would get Fn is equal to the number I got to 3 significant digits is 4.22 times 10 to the third newtons. Okay, one more. So we're back to taking an object and swinging it in a vertical circle. So if you want to imagine something, you could once again imagine just a rubber stopper with a string through it and swinging it in a vertical circle that would cut into the ground perpendicular. A, what point in the circle does the object have the greatest chance of falling out of the circle? And then B, determine the minimum speed required so that the object remains moving in a vertical circle. Okay, this is a bit difficult to explain without doing a proper illustration. Just imagine yourself with like a rubber stopper on a string. You start spinning it like really fast. And if I told you to start to reduce the speed at which you're spinning it, like sort of get slower and slower and slower, and I want to approach the point where I'm spinning it at like the minimum speed where it's still going in a circle, where's it most likely to fall out of the circle? Well, if you actually went ahead and did that, it would be at the top of the circle. The problem is that at the bottom of the circle, so if we drew like a free body diagram at the bottom of the circle, to stay in a circle, we need tension. So at the bottom of the circle, you'd have like Fa that points up, and you'd have the force of gravity that is down. What the force of gravity would do is the force of gravity, since it's down, would actually stretch the string. So it would actually help in keeping the string taut. If you looked at a free body diagram at the top, which we'll do in a second, I'll do a more official one in a moment, you'd have both Fg and Fa pointing down. So they're kind of both pointing in a direction that is going to result in the string no longer being taut once you've reduced the speed at which you're spinning it. So the top is the greatest point where you have a risk. Okay, so I'll just say this. At what point in the circle does the object have the greatest chance of falling out of the circle? The object has the greatest chance of falling out of the circle at the top because FG is not helping keep the string taut at this position. I'm sure there's some other explanations you could use to justify this, but that's what I'm going to go with. At the bottom of the circle, FG helps stretch the string. At the very top of the circle, it's not helping out. So once you reduce that speed, it's more likely that the string is going to like fold in at the top because FG is not helping out with that. All right, so determine what this minimum speed is where we can continue to move around in a circle. Okay, so we've identified top is the critical point. So we'll do a free body diagram at the top. And our mass acceleration diagram. Once again, we'll just draw this in a different color. Okay, and we'll draw the object, do the MAD first. Use M to represent the mass. My centripetal acceleration always points towards the center of the circle. And then at the top of the circle, you would have two forces. You'd have the force of gravity that points down, and you'd have the tension force, Fa. Let's write down our equation of motion, which is actually going to be identical to the derived equation of motion from the first example at the top of the circle, except we're going to make a modification to this. So we're looking at the centripetal direction. So sigma Fc is equal to MAC. Again, that's our uniform circular motion physics principle. If down is positive, then that means that Fg would be positive, Fa would be positive, and that would be equal to M times positive AC. Let's go one step further, and then we could have Mg plus Fa is equal to M, and we want to calculate speed. So the equation we're going to plug in for centripetal acceleration is going to be the one that's Vc squared divided by R. So we have M Vc squared over R. Okay, I got a couple of problems with this step. First of all, the question didn't give me a mass. And secondly, well, what's this tension? Now, think about this. If you take this rubber stopper and you spin it around in a circle, and you spin it really, 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 really fast, the faster you spin it, the greater the tension is going to be in that string. As you start to bring this rubber stopper to a slower and slower and slower speed, that tension is going to get smaller and smaller and smaller. When I approach that minimum speed, the tension of that string is almost zero. Maybe not quite zero, but close enough to zero. So I'll say at the minimum speed, Fa, so that saying is equal to zero. I'll use little squiggly lines from an equal symbol. It means it's approximately equal to zero. So the minimum speed would be like that, kind of like that last point where you'd have any tension, but that tension is so ridiculously small. Okay, let's see what happens to the equation now when we do this. So if Fa is pretty much zero, then let's just get rid of it. And then I'd be left with Mg is equal to MVC squared over R. Well, now if I divide both sides of the equation by M, the M's would cancel off. Okay, let's rewrite this equation now because it's looking kind of complicated with all the crossing out. So then we'd have G is equal to V. Let's change the V to V minimum. V min squared over R. To calculate the minimum speed, multiply both sides of the equation by R and then take the square root, and you'd have V min is equal to a very simplified equation. Again, this is all the more reason that of why you don't want to plug numbers into an equation until you get to the end of the problem, because oftentimes things cancel off. Okay, we're given radius here, 0.85 meters multiplied by 9.81 meters per second squared. And then the minimum speed would be, I got 2.9 meters per second. It's interesting to note that like the problem solving procedure we've been using, so pretty much like very early on in the dynamics unit, I taught you how to draw FBDs and MADs and how to derive equations of motion. And it's crazy like how long we've been using the exact same problem solving procedure to solve like these different problems. So you can kind of see here like the power of drawing free body mass acceleration diagrams and then using them to mathematically model situations. So here we can also use them mathematically model uniform circular motion. And this is something that in later physics courses we'll continue to use, this idea of free body mass acceleration diagrams to build equations that mathematically model the situation. All right, so that's the end of the lesson, and you can complete the assignment called vertical circles. And then in the next lesson, we're going to shift gears in the unit. So the first part of the unit deals with uniform circular motion. And then the next part of the unit, we're going to start to focus on the gravitation aspect of the unit.